Only 4 PowerPoint slides, but they're super important, okay? First way to get wave speed. Second way to get wave speed. If we know the frequency and the wavelength, we can automatically find the speed of the wave, okay, the velocity. All right, now I try not to give you guys physics equations and just say, trust me, it works. I'm a physics teacher. Trust me, it works. Okay, we always try and talk about either where it comes from or prove it in some way. All right, so one way to prove if an equation works is to do something called dimensional analysis. Okay, does anybody know what that means? Yeah. 2D versus 3D. Okay. Yeah, it's not so much about like third dimension and all that. It's about units. Okay, it's about proving that the units work out. Okay, so both sides of this equation have to have the same units. What unit should they be? Yeah. Okay, so V equals F lambda. Let's look at the units. Okay, this is probably a good idea to write down. So we know that that's meters per second. We need to prove that this side comes out to meters per second. So let's do that. Oh, by the way, we're on the back of your note organizer from last time, where it says wave speed notes. We're not on the new one.
Frequency is waves.
Okay, so what is frequency? Frequency is how many waves you have per
Second.
You got waves per second. Okay? Now, usually we shorten this to hertz. We can also call it waves per second. Now, wavelength is how many meters a wave is. It's how long a wave is. And in math, if I have x up here and x down here, what happens to it?
Cancel.
Nice. Cancel, cancel. We love canceling stuff in physics. It makes our life easier. Okay, we simplified it. Now I got meters over seconds. Okay, the other way to look at this is frequency is the same as 1 over the period. Okay, and period is in seconds, so we'd have meters over seconds. That's the other way to kind of look at this equation. All right, so depending on the situation, this might apply, or if you know frequency and wavelength, that applies, and you can just use that. Okay, now that's the easy part. I know you guys can throw numbers in there and do some math. No big deal. Okay, you need to know how to use this and when it applies, okay, and how all the conceptual stuff that goes with it. Okay, so 2 important facts. Here's the first one. All right, so a couple examples. This constant velocity thing. A couple things have to be true. Number 1, we have to have the same type of wave and the same type of medium for this to be true. So let's talk about sound. Let's say we're doing a lab in here and everybody's talking. You got some low-pitched voices and then you got some high-pitched voices. Okay, which one goes faster? Let's say we got music playing as well. So we got voices, music, sounds, loud sounds, quiet sounds. Which ones go faster? All same. All the same speed, which is crazy. It's one of those misconceptions we need to untrain our brains.
There's the speed of sound, right? So
There's the speed of sound.
The speed of sound because it's sound.
Yes, if it's all sound and it's all in the same medium, all same speed. Okay, louder sounds don't go faster. Higher pitch doesn't go faster. So the type of wave sound, the medium would be air. All right, and everything goes about 700-ish miles per hour in air. Okay, and then the temperature affects that. We'll get to that later though. If the temperature affects it, then we've got a different medium, we say. All right, what about light? What about the colors? Okay, the whole rainbow of colors going through space. Okay, do they have different speeds? All same speed. Okay, they have different wavelengths and they have different frequencies, but they all go 3 times 10 to the 8 meters per second. Really, really fast, lots faster than sound. Now we bring the whole rainbow, and we're looking at a rainbow caused by a storm or something, okay? And that is coming to our eyes through the air, and light actually travels a little slower through air. The speed goes down a little bit, just a little bit. Okay, all right, questions about that? Anything? I bring up
Does it get slower as the medium gets thicker?
It's with density. As the medium gets more dense, the speed of light goes down. All right, in glass, in a diamond, it's the slowest that I can think of or that I know. All right, diamond is very, very dense. Light slows down quite a bit. Okay, all right, now, a consequence of this is this next fact. This is very important to have down. In other words, if one goes up, the other goes down. That's all that means. And we'll do a good picture here in a second, so help us understand that. Here's a couple waves. Going the same speed. One is not catching up to the other, accelerating past, all right? Same speed, they're moving together. Okay, here we've got a higher frequency than this one. What do you notice about the wavelength up here? Okay, lower wavelength, and then we've got a higher wavelength down here. Mathematically, let's say the velocity of each of these is 4. Okay, let's say they're going 4 meters per second. If this is 4, and for this top wave this is 4, what's lambda have to be? It's got to be 1, because 1 times 4 would make 4 over here. Okay, now down here, if the frequency is 1, what's the lambda have to be? 4 to make the equation true. All right, same speed. We're going to do 2 examples. We're going to kind of do some of the math of this. All right, and we're going to use V equals F lambda for this. Okay, so let's say we got like a puddle, and we put a pencil in that puddle and count the waves that go by. Let's say we find 3 go by every 1 second. And then maybe in the picture we measure that out to be 2.5 centimeters. Find the wave velocity. Okay, try it on your own and then I'll show you if you're right.